Okay, thank you for the intro, and thank you to the organizers for the invitation. It's been a very nice conference so far, and I'm always happy to be here. So what I want to talk about is joint work in progress with Preston Wake. It's a little bit preliminary, so I mostly want to just talk about an example that we've computed things, but I think the example already tells a very nice story and kind of indicate where we sort of want to go from here. So I want to start with this example, which is quite well known, but maybe not by everybody in this room. So I want to look first at the space of weight 2 modular forms on gamma 113. Okay, this is my favorite space of modular forms right now. This is two-dimensional. This is a two-dimensional space spanned by new forms. There's a new form F. Let me write down what its Q expansion looks like, at the start at least. Q plus, I don't have my notes for this, negative zeta 6 minus 1 Q squared plus 2 zeta 6 minus 2 Q cubed, etc. You can look this up in LMFDB. Okay, so this modular form has coefficient field. I should have divided my board in half. Well, let's at least use a little bit of space here. Coefficient field Q adjoin this primitive sixth root of unity, which is of course the same thing as Q adjoin a primitive third root of unity, and that's just Q adjoin square root of minus 3. So it's spanned by this new form and its Galois conjugate. Okay. Now what I want to do, see these on my boards? Okay, this is the next one. Okay, so F has an even typus, so what's going to be important here let's call it eta, Z mod 13 of order 6. Okay, and what I want to do now is I want to consider the mod 3 Gala representation associated to this F. So take the reduction modulo of the square root of minus 3. So let's let rho bar from GQ to GL2 F3 be the mod square root minus 3 representation associated to F. Okay? Now this is absolutely reducible. And the determinant, rho bar, okay, well, it's weight 2, and this is this Neven typus, so the determinant is given by the mod 3 cyclotomic character inverse with the normalizations I want to use, times the reduction of eta bar. So epsilon will be my notation for the triadic cyclotomic character. And I just want to point out here that this eta bar is quadratic. Right, it had order 6, and we took its reduction modulo 3. Okay. So now why is this example interesting at first glance? So we had a couple of talks about Serre's conjecture so far today. And now if you look at Serre's Duke paper where he formulates the weight and level part of Serre's conjecture, he actually also in that paper just said that you should also be able to take fix the Neven typus as being the Teichmüller lift. However, he himself quickly realized afterwards that that's not quite always true. And this is the example. So this is Serre's example that says that you can't fix the Neven typus to be the Teichmüller lift. Because you see what happens is if you demand this to lift to something that is weight 2 on gamma 113 with quadratic Neven typus, that space is 0. because I just told you this is two-dimensional and only has two forms that both have Neven typus of order 6. Okay, so you can't do that. But so what does that mean? I want to say what that means in terms of sort of Eichler-Schmor and cohomology. So let me set this up farther. Okay, so that means the following. I'm going to define this sort of intermediate congruent subgroup. So let me define this gamma between gamma 113 and gamma not 13 such that gamma mod gamma 113, I'm going to call this delta, and this is order 3. Okay, so it could go order 3. And now, oh, sorry, I forgot to say, I really want to be explicit, so it's really important. I want to mention for what I want to say is that rho bar is absolutely reducible. I didn't say it above, but let me say this is important. So let's let M inside, I'll define some sort of universal Hecke algebra, which will be, really like the way I've done that. Let me go down a little bit more here and say a maximal ideal inside some universal Hecke algebra, which for me will be, oh, I didn't introduce, so I'll call it O, formal symbols, TV, or TP, diamond P, for P not equal to 3, 13. B, the non-Eisenstein maximal ideal associated to rho bar. And here my O, this will be my coefficient ring, which in this example will be just the root 3 adic completion of the ring of integers of the coefficient field of my modular form, which is the same thing as Z3 adjoint a primitive third derivative unity, say. Okay. Then, what I want to say, first degree cohomology for gamma with coefficients in F3 localized at M is non-zero, but cohomology for gamma with coefficients in O localized at M is 0. Okay? This is the result that you get from this. By the fact that you have a mod 3 modular form with this quadratic Neven typus, so it lives on, it's associated to this group, right? But you don't have one in characteristic 0. Okay? We don't want to take, so I think this is the forward one. Very good. Okay. But now if you look at the sort of standard multiplied by uniformizer exact sequence on cohomology, mapping O to its residue field, what you deduce is that you have this non-Eisenstein maximal ideal in the support of an H2. So then this implies that H2 of gamma with coefficients in O supported at this non-Eisen maximal ideal is non-zero torsion. Okay. Now, where does this come from? Well, it's actually not so hard to see what's happening here. Is that if you look at the Serre-spectral sequence, right, you have some HI delta HJ gamma O. Local. I'm going to erase something here, so if you're taking notes, please wait a minute. Okay. Oh, sorry, not gamma. Gamma 113. Sorry, this O is localized at M. Now we know what level gamma 113 right? When we localize it at a non-Eisenstein maximum, everything dies except for the H1. So really what this class is this is coming from an H1 of this finite group acting on the H1 at level gamma 113. So this has to be an isomorphism. But now if you have a finite group and you have non-zero cohomology in degree 1, you also have non-zero cohomology in all odd degrees, right? Finite cyclic groups, right? Finite cyclic groups have this periodic cohomology. And so then you end up deducing that Hi gamma O with this non-Eisenstein maximal ideal is non-zero torsion. For all odd I bigger than or equal to 1. Okay? So now, this may be a little bit of funny behavior if you haven't sort of thought about this before. So let me just say the remark. I mean, obviously, one of the things that's happening here that's driving this is that this subgroup gamma has 3 torsion. Sorry, what's that? Oh, yeah, thank you. Yes, of course. Sorry, yeah, I'm getting, I was getting my index here confused with the index here. Thank you. This delta is cyclic, finite cyclic group. Sorry, this. So I'm saying that because this, whatever this is, let's call this M for a second. Because H1 delta M is non-zero, H3 delta M is non-zero, H5 delta M is non-zero. But you look at the same spectral sequence, computing this. Yeah, even bigger than equal to 2. Yeah, exactly. Okay, so this is 3 torsion. And in fact, it's even a semi-direct product. And I'll have to check my notes to make sure I write it the right way. I hope this is correct. Okay. So it's not surprising then, I mean, it's a well-known thing if you have an arithmetic group that has p torsion, it's sort of p cohomology is going to have things in infinitely many degrees. But at least what was surprising to me at first is my first guess is that these torsion classes that appear for these kind of orbifold reasons would be Eisenstein, right? That's a natural first guess. But it's not in this example, okay? And in fact, you can see other examples. This Ribbit has a paper where he analyzes component groups of Jacobians back in the 90s, showing similar phenomena. That your first guess is that things are always Eisenstein, but no, they're not. However, it's pretty close to being Eisenstein. I'm going to come back to that. It's about as degenerate as a non-Eisenstein maximal ideal can be. And in particular, what Carryall tells you is that this can only happen if p equals 2 or 3 and rho bar is induced is an irreducible induction of a character in the p equals 2 case q adjoin I and the p equals 2 case q adjoin square root minus 3. This is the only times this can happen. Okay, are there any questions about this? No? Okay, good. So, all right, that's all I wanted to say about that. So I think, no, this one maybe goes up to the top. Maybe I'll bring the middle one down. That's the right way to do things. Okay, so I want to sort of switch up and talk about something a little bit different for a minute for the next part of my talk. I want to talk about presentations of Galois deformation rings. Okay. And I want to circle back and link to this example later. So let's say I'm in a situation, I want to do let's just say f is totally real. And let's say I fix some sort of coefficient field. Finite. P will be a prime. I'm not going to talk about p equals 2 today. Always odd. O, the ring of integers. O, E. And F, the residue field. Var pi uniformizer. And OK. So now let's let rho bar GF to GL2F be absolutely irreducible and modular. Let's assume it comes. So in the most basic way, let's say it comes from some Hilbert modular forming characteristic 0. We take its reduction, this Gala representation. OK, so let's say, I'm actually not going to be precise, say rho bar satisfies the Taylor-Wiles hypothesis TWH if its restriction to the field where you join a p-th root of unity is still absolutely reducible. And I don't know. I don't want to be precise. So the thing is whenever somebody says the Taylor-Wiles hypothesis in the literature, it's kind of a fluid concept. It kind of depends on the paper you're reading. It changes around a little bit. But the part I want to focus on is this, which at least if we take the example of f equals q and p odd, this is unambiguous. This is the Taylor-Wiles hypothesis. Okay? Now for a totally real field, already there's a little bit of issues as to what you assume at 5, and there are different iterations of it, but that won't be important for my talk. So you can ignore that. All right, well, this is sort of quite ubiquitous, some sort of hypothesis of this form. Sorry. Yeah, so what I'm saying is that this is essentially enough when you're in GL2. Now, when you go to higher rank, then it becomes even more fluid because there's these various things like, enormous, adequate, big, that are all different for rank higher than 2, but they're all the same in rank 2. So really, this is enough. But there is a subtlety for p equals 5 particularly, somewhat for p equals 3, although it's less of an issue with something else that comes up. But like I said, I don't want to talk about that. OK, so which board am I bringing down? This one, I think.
Are you making any local assumptions on F? I mean, could F be F?
Sorry, what's that? If?
Are you making any local assumptions about the ramification of P in F?
Not right now.
So F could be F. It's totally real.
It's totally real. I did say totally. Yeah, I did say totally real. Yeah, exactly. Yeah.
But it could be different.
Yeah, and that's very important. Absolutely. Yeah. Yes. George knows exactly where I'm going with this. Yeah, that's exactly the sort of situation I want to distinguish between, whether the quadratic extension is f zeta p or not. That's important. OK, so let me say, what is the Taylor-Wiles hypothesis used for? Well, it's used, obviously, I mean, the main thing is used to prove modularity. But also, let me say another thing I'm interested in is sort of geometric or commutative algebra properties of Galois deformation rings. Right? So for example, let's just say f equals q for simplicity because the statements are much easier in this situation. So both these examples, I'll just say when f equals q. So 1, sort of Wiles, Taylor-Wiles, Diamond, and others prove things like certain small, I won't make that precise. Let me just say things like deformation rings are finite flat complete intersections over whatever your fixed kind of base coefficient ring is. Okay. And in another direction, Buckle proved, colon here, that certain sort of big, and let me work in the, let me just say fixed determinant Galois deformation rings are O-flat reduced complete intersections over O of the expected dimension, of dimension 3 in this case. Okay. All right, so I want to say that, I mean, these are sort of theorems that I think are interesting in their own right. They're also useful for some things. And in sort of the Taylor-Wiles hypothesis will appear in both, just because, but I mean, you sort of, one of the things I'm sort of interested in is how much is this an artifact of the proof, how much of these things are necessary. And it's sort of clear that they have to be just an artifact of the proof because some things are conjectured to hold, whoops, forgot, even without it. So you think also analyzing the proofs that this is just clearly just a way to sort of get by. But then there's something, in a lot of these situations, one of the things that's really important or really useful to understand is the relation between some global Galois deformation space and some local Galois deformation space. Okay. So it's often, so in either situation, sort of useful or important, depending on what you're trying to do, to analyze or to use, to understand maybe, sort of a map the map from a local deformation ring to a global one. Okay? This is always sort of pretty much always present. And so let me just be a little bit more precise what I mean by local one for a second. Okay, so say S is a finite set of primes of F containing the set of all V, let me move this down here, containing the set of all primes dividing P, and also the ramification set of our row bar. Okay, then when I mean our loc is, say, a completed tensor product over all of these, RV, where RV is a, and maybe, it's not important, but maybe you need a framed deformation ring for row bar restricted to the local Gala group. Okay, and what's the first thing you can do when trying to analyze, when I said you want to understand this map? Well, I mean, one of the standard things you look for is a presentation. I think this one goes up, this one comes down. Okay. Okay, so basically, essentially, Buckle and Kissen kind of tell you that there exists a presentation in the situation as I've described it, are global, isomorphic to our local, x1 up to xg, modulo relations f1 up to fr, with, in the above situations, in above, let me just say in favorable situations. Let me say, so when I haven't been precise here. I just said this is some local deformation ring. I don't want to take just like an arbitrary ring here. I don't want to take some arbitrary quotient of the universal thing. You want to sort of take something that's somewhat nice. So the two situations I'm sort of motivated by, or think you should keep in mind, are these in the situations of 1 or 2 above, where either you're taking some universal thing, or maybe you're taking some quotient that corresponds to some, p-Adicodge theory with regular weights, or maybe at the primes not dividing p, you have some union of irreducible components, something along those lines. So in situations, so let me just say in situations as in example 1 and 2 above, what you get is that this presentation is such that, let me write this out, is that the conjectural dimension of R global is equal to, and you usually can compute the dimension of R local, plus G minus R, and then, let me make sure I got my sign right, minus the dimension, well actually let me write this down maybe so I can write a bit more, minus the dimension of the H0. Now I'm going to use trace 0 endomorphisms. I might as well define this in case people aren't familiar with it, of the add 0 rho bar 1. Okay, what I mean here where here add 0 rho bar equals trace 0 subspace of endomorphisms f rho bar, and this 1 is a Tate twist, right? Okay. So what I want to say is that if this vanishes, right, then you get exactly a nice presentation of this, giving you the expected dimensions. So you end up with the expectation, then, is that our our global is a local complete intersection map if this H0 f add 0 rho bar of 1 vanishes, right? Because then you have a presentation in hand giving you exactly the relations. Yes? Sorry. But this is presenting over our log. Right? So then this should be generator modulo regular sequence to get down to our global. I think this is okay. Okay. And equivalently, I just mean that, yeah, this F1 to FR should be a regular sequence here in this presentation. Okay, let me spell out what this is, right? This is exactly what George was sort of commenting a minute ago. When does this not vanish? This happens if and only if rho bar satisfies the Taylor-Wiles hypothesis, but it's actually more. So Taylor-Wiles hypothesis and, actually, I didn't want to say this. I wanted to phrase this unless. Sorry, I'm going to change this. Unless this is not equal to 0. Sorry, this is a little awkward, but it's easier for me to state this way. I don't want to say an or. I want to say that this is not equal to 0 if and only if rho satisfies the Taylor-Wiles hypothesis and the degree of f zeta p over f is 2. It's easy to sort of work out. Okay? And this is, in the terminology of Buzzard-Diamond-Jarvis, their Serre-Waite conjecture, is what they call badly dihedral. Right? Because the Taylor-Wiles hypothesis is exactly saying that you're not induced from the... So let me just spell out. What is this having fixed vectors here? Well, if you think of this, right, as a space of Helms from rho to rho, rho bar to rho bar, its Tate twist is space of Helms from rho bar to its Tate twist. Right? So if you have a non-zero vector in there, that's exactly saying you have an isomorphism from this to its Tate twist. But if you're isomorphic to, then you're reducible when you restrict to the cyclotomic extension. And that tells you you have to be dihedral, but then the fact that you have an isomorphism forces that Tate twist to be quadratic.
You don't formally mean this. You mean if rho bar satisfies Taylor-Wiles, then the equivalence is to this being 2.
Sorry. Yeah, I'm trying to just say what this condition means. Oh. Oh, yeah. So no, but I changed this to a not equal to 0. So I think I just,
You assume that to start with it satisfies Taylor-Wiles hypothesis, and then this being 0 is equivalent to what George says.
Yeah. So I wanted to write this is a complete intersection unless this is non-zero. And then, I agree, it's awkward. Okay, so sorry. Let me. So this is a little bit, okay.
Just erase rho bar satisfies Taylor-Wiles because you already assumed it, and that's fine.
No, I didn't assume it. I just gave a definition. Yeah, I just gave a definition. Like, we say rho bar satisfies Taylor-Wiles, but I actually don't want to assume it.
Rho bar is 1 plus cyclotomic or 1.
I assumed it's absolutely reducible. Yes. I mean, yeah, sort of, yeah, I should say. So, okay, let me say if this happens, and then let me just move this to a new board to make things more clear. So I assumed rho bar was absolutely reducible, and then I said, we say it satisfies the Taylor-Wiles hypothesis if blah, 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 blah. Okay. Which board do I want down? Sorry. Oh, now I need this. Yeah, you're right. Yeah, okay. Yeah, if I'm changing this, thank you. Yeah. Thanks. Okay. So note H0F add 0 rho bar 1 is not equal to 0 if and only if rho bar does not satisfy Taylor-Wiles hypothesis and f adjoins zeta p over f is quadratic. Degree 2. Okay, and now that I have extra room right here, now I might as well at least write down. This is what's called badly dihedral in the paper of Buzzard-Diamond-Jarvis. All right. And then the question is naturally, I want to know, so, I mean, you get this expectation based on known conjectures. You just plug in this presentation into known, sort of existing conjectures, you get this expectation. What's more interesting is if the converse is true, right? If this is really a characterization. So the question So it does H0 F at 0 row bar 1 not equal to 0 imply our loc to our global not a local complete intersection. Okay, that's what I think is a little bit more interesting. But before talking about that, let me just state at least something you can show as far as the expectation goes. So first, so here's a proposition. And I don't want to claim any originality here because this is essentially, you basically plug in some results of Louis-Pan into Gebhardt-Böckle's method, and this result sort of pops out, is that let's say we assume, so I'm going to work with f equals q. I mean, I'll be explicit, but might as well emphasize that at the start. So let's take f equals q, and p bigger than or equal to 5. So in particular, this does not hold in this situation. Really, this is really larger than this. And rho bar is an irreducible induction of a character on the quadratic subextension of q into q zeta p. What word did I finish off? An irreducible induction. I should have said of instead of on, but okay. Sort of. I'll say of a character on G, Q, adjoin. Now this field is -1 to the p minus 1 over 2 square root p. Okay, this is the quadratic subfield. So then let's say, time to go. Let's let, say, C from GQ to O cross be a de Rham character lifting determinant of rho bar. Let's let our global equal the determinant, the universal determinant equal to the C, deformation ring, unramified outside S. And RV equal the local, right, the universal local, fixed determinant C as well. Then our global is an O flat reduced complete intersection over O of the right dimension. Dimension 3, and thus this map, our local to our global, is a local complete intersection. Okay. Just determinant. Yeah, I'm doing the big universal thing.
So even for the local, it's just frame deformations with no conditions?
Yep. Yeah, exactly. Yeah, just the determinant, that's all. I mean, so I think we could probably also do similar things for some finite one, but I just did this so far as a test case. Okay. Any questions so far about this? Okay. So basically, the point is I just wanted to sort of, check that you can have something violating the usual Taylor-Wiles hypothesis, but not in a bad way, violating it in a very mild way, such that these same sort of situations hold. Okay, but as I said before, I think that this other question is more interesting. So unless there are any questions about this, I want to return to the example from before. Okay, so example revisited. So let me recall the notation I had before. Okay, so remember O is zeta 3 giant cubed root of unity. Let's see, and F. So rho is equal to rho bar F square root minus 3 from GQ to GL2 F3 for F inside S2 gamma 1 13 O as before. Sort of M again, universal, the associated, non-Eisenstein maximal ideal. Okay, so now I want to set up my deformation problems I want to look at. So instead of calling it R global, let me just call it R. So this will be the global, this will be the deformation ring. For, well, deformations of rho bar unramified. Oh, sorry. No, before I do this, actually, it's important. Let me say. So let's recall also the determinant of my rho bar. So this is the mod 3 cyclotomic character inverse times a quadratic character. I want to give that quadratic character a name because it'll come up later. This is delta 13. Where delta D equals quadratic character associated to Q adjoin square root D over Q. This is sort of what the Nebben typus is, modulo 3. So let's let R be the deformation ring. Sort of the deformation ring for deformations of rho bar unramified outside 3 and 13. 13. Okay. With determinant equal to cyclotomic character inverse times this quadratic character. And that are ordinary finite flat at 3. Okay, so things that in characteristic 0, ordinary, Hodge-Tate weight 0, 1, crystalline condition. But no condition at 13. Okay, so this one bit, and then we say R13 be the universal, technically speaking, right? We want framed here, framed deformation ring of rho bar restricted to GQ13, but with fixed determinant epsilon inverse delta 13. And then I'm going to consider a quotient I call R13 min. This would be the quotient of R13 corresponding to minimally ramified lifts. So what does that mean? So it's rho with rho restricted to inertia conjugate to 1 and then this delta 13, this quadratic character. Okay, so I'm not allowing this to deform. Okay. Okay, any questions about the setup?
Sorry, can I ask you something?
Oh, yeah.
The
Yeah.
position that you mentioned, but is there
Yeah.
some restriction on the weight? Because I know that sometimes the algebra is not even Galois time, right? If K is P or something.
Well, yeah. So I did a universal thing, right? So there's no weight here. So the universal thing is conjectured to be an O-flat complete intersection over O. Yeah. So in general, this is a good question. So what if you cared about, this is a good point. So what if you cared about the first sort of example I said, where you have some small deformation ring and you want to understand whether it's local? That's exactly right. It's not expected to always be a complete intersection over O, right? But what I'm saying is, what should happen, at least if this sort of H0 of the adjoint 1 vanishes, is that the reason why it's not a local complete, the global thing is not a local complete intersection is only because of the local thing is not. So it should be the case that you can always present the global thing over the local thing in some sort of complete intersection way, but then whatever singularities, any extra singularities like not a complete intersection but Gorenstein, et cetera, or not even Gorenstein should just be coming from the local deformation space. Okay. Are there any other questions? Okay. Yeah. Okay, now where did I leave? Oh yeah, here. Okay. So this is my setup. Okay, so now.
Can you ask if the
Oh, yeah.
deformations be diagonal on the measure 13, or is there a star?
They will be diagonal.
They will be diagonal.
They will be. Yeah. So that's actually, that's important in the proof of what I'm about to say. But yeah. So it's exactly because this will be some sort of distinguished representation, and you can prove, kind of similar to how in the Taylor-Wiles situation you prove that every lift has to be diagonal. They also will be here. Yeah. The universal lift is in fact will be a direct sum of characters, which is important for what I'm going to say. Yeah. Okay, any other questions? Okay, then. Here.
Delta 13 is like eta cube, so what you're avoiding is like to have like eta and eta square kind of things on the diagonal.
Sorry, can you say again?
You fix the determinant, so what you're really avoiding is like to have like eta and eta square on the diagonal, because delta is like eta cube, right?
Delta is eta, no, I thought delta was supposed to be eta bar. I thought this delta was supposed to be the quadratic character associated to.
Eta is order 6, so delta is like eta cube.
Oh yeah, okay, yeah, but.
So what you want to avoid is like having eta and eta square on the diagonal.
Well, what I'm saying is that this modular representation, like its mod 3 reduction, has this restriction.
Right.
And so this is the minimal condition where I want to say there's no deforming. So in particular, the modular form F would not satisfy this problem.
Yeah, so
Yeah.
my question is how is F is like two other powers of eta, because you fix the determinant, right?
Yes, well, yeah, I fixed the determinant. So yeah, exactly. So if you look at the standard Galois representation associated to F, it would look like 1 in eta, but then I'm going to twist it by the order 3 thing in order to fix the determinant. Yeah, exactly. Okay, any other questions? Okay, so then the theorem. So as I say, this is the one result we've certainly computed that we hope to do more, but I want to state what I know we can do for now. So is that, I prefer to work with homology in this formulation. So I'm going to say that for the same group I defined before that lives in between gamma 1 13 and gamma not 13, this is a free module over the Tor algebra, where I take Tors with respect to the universal deformation ring at 13 with the universal minimal deformation ring at 13 and this global deformation. And in fact, this is isomorphic to O mod 3, polynomial in one generator, where the degree of x is 2. Okay. So this is the result. Now, I want to circle back to the Galois side when I was talking about local complete intersection maps. Remember that if you have a local complete intersection map, by the causal complex, you know that anytime you take Tors with something, you're going to just have a finite range. So one way to test that something is not a local complete intersection is if you can have some infinitely many Tors, which is exactly what we're doing here. And moreover, we're showing that, in fact, this cohomology that appears in infinitely many degrees coming from this non-Eisenstein prime is actually, you can think of on a Galois deformation theoretic side as arising from these Tors. So there's some sort of, non-complete intersection happening in local deformation space that is the Galois theoretic account. And so this is sort of in line with some of the philosophy that's, been expounded to great degrees by Caligari and Garrity and Venkatesh. But it's happening for a totally different reason. It's happening for these sort of like degenerate stacky reasons, right? These orbifold points. But the thing I want to emphasize is that in a correctly formulated R equals T or cohomology is free over a deformation ring is still true in these degenerate situations, right? You still have this freeness if you formulate things in this way. Yes?
Can you interpret this action as X as some kind of derived technical operator on the
Yeah, that's a good question. So it's going to be very apparent in the proof where this is. So in fact, these are just diamond operators that are happening. And this is totally transparent because how do you compute this cohomology? I'm going to about out of time, so I'm just going to sketch this very quickly, is you resolve this, right? This homology, right, is just taking covariance, derived covariance with respect to the diamond operators. But that's exactly what's going on here, right? Going from the 13 down to the minimal is exactly derived covariance, and I'm just taking the derived covariance here. So that's why. So it's totally transparent what's happening. Are there any other questions? Okay, so let me just say very quickly, at a time. So sketch is that, well, right, this homology is computed by as I said before, you take derived coinvariance with the first homology at level gamma 113. OM. Some SEM. Okay. So let's take your favorite finite free resolution of O. So let P O be a resolution by finite free O delta mods. Okay, so then what you show is that there's a natural map from O delta. So as I was saying to David's question, is that you prove that the universal deformation ring at 13 is actually split, direct sum of two characters. So you have this map, right? And you prove that it's formally smooth. Right, this is formally smooth, hence flat. And right, the coinvariants are exactly going to give you this minimal deformation condition. I'm getting myself confused as to which board to use. Okay, so then.
Just move that down a bit so we can read the last line.
Oh yeah, sorry. Yeah. In fact, yeah, I'll keep it down here for a minute, just to make it extra clear. So then if I take the tensor over O delta of R13, this is a projective resolution. Right? Because since it's flat, if I tensor, this stays flat, and I took finite free things, so these are all going to be some finite resolution by finite free O modules of this. But then what that tells you, then this homology star gamma O m is computed by P tensored over O delta H1 gamma 113 O m. But then that's the same thing as if I take P tensored over O delta R13, then tensored over R13 with H1 gamma 113 O m. But this exactly leads you to Tor of R13 with R13 minimal and this first homology group. Gamma 113 O. Oops, there's an M here, then a closed parentheses. Okay? Yeah, exactly. Sorry, I didn't, because I was sort of getting a little bit, rushed for time, being a little spastic, it's sort of, I forgot to write that. But. Okay, and then so what it remains to prove, so, and actually maybe in some sense a lot of the work goes in here, then we prove that this homology at level gamma 113 is finite free. I mean, it's in fact rank 2, I think, but finite free R mod for the deformation condition I set up before. Let me say using Wiles' criterion. So we're in a situation, right, where we can't use Taylor-Wiles prime, so we can't use that story. However, we can go back to Wiles' criterion and actually apply it in this case. Because, as I said, so this representation, this mod 3 representation is non-Eisenstein, but it's highly, highly degenerate. And in fact, its add 0 breaks up as a direct sum of 3 quadratic characters. The one corresponding to -3, the one corresponding to 13, and the one corresponding to -39. And so we compute the H1F of this add 0. I mean, really by hand, using some sort of class field theory. And we compute the sort of the cotangent module that appears in Wiles' numerical criterion and show directly that way that this is in fact an isomorphism. So this is sort of the sketch. Let me just say the couple of remarks is that, something that came up, for instance, in Alicia Pozzi's talk is, a very nice thing in our theory in general is sort of a tame versus p-adic dichotomy. And we expect that we might be able to show that this also arises as a sort of a derived intersection at p, using the fact that this rho bar actually has an ordinary lift at level gamma intersection gamma naught 3 in characteristic 0. And then taking some sort of intersection where you have some sort of ordinary weight 2 deformation ring with no crystalline condition and then intersecting with the crystalline quotient. And I'm sort of hopeful that similar phenomena happens also over totally real fields anytime you have this quadratic extension. But what happens in higher rank is less clear to me. Not really sure what's going on. So thank you. I'll end here.